Hello, my dear students. Welcome to the 8th lecture on particle physics. Yesterday, we were discussing about the exact conservation laws, and we shall start from there. We discussed about the energy and linear momentum conservation laws, and what I had promised that first we will discuss threshold energy of a reaction before moving ahead. Now, what is threshold energy of a reaction? Suppose I am talking about A plus B going to 1 plus 2. Okay, like I am talking about a reaction pi minus P going to pi 0 n. Then what should be the minimum energy of the reaction to have pi 0 and n in the final state? Or if I take another example where we have an electron beam and a proton as the target, then what minimum energy we would require to have a neutral pion also in the final state, or besides a neutral pion, a pi plus and pi minus, or in general you can say that I want to have n pions in the final state taking care of the charge of these particles, because we cannot violate charge conservation. Therefore, we can have pi plus, pi minus, then again a pi plus, pi minus, or we can have 4 pi zeros in the final state. Therefore, this threshold energy is the minimum energy required to execute a reaction. That means to have the desired number of particles in the final state for a given initial state. For example, if I am talking about a target particle, say this is my target particle B and my projectile is A. Now this target particle is at rest. Therefore, its energy is its rest mass in units of C and H cross. Again, I am using natural units. And what is its 3 momenta? 3 momenta is 0. While this guy has both energy and momentum. Okay. Therefore, I have A plus B in initial state, and then I want to have 1 plus 2 as the particles, A, B in the initial state, and 1 and 2 as the particles in the final state. Now, from energy conservation, we have EA plus EB. That must be equal to E1 plus E2. This we have discussed yesterday. And PA plus PB, that should be equal to sum of the linear momenta of the particles in the final state. These two are coming from the energy and linear momentum conservation. Now, these together we can also write it as PA plus PB must be equal to P1 plus P2, or in terms of 4 momenta, which has the energy component and the linear momentum component. Therefore, if I square this, then I will have a square of that also, P1 plus P2 whole square. And then in my next step, I am going to write this guy as the energy part, EA plus EB whole square, minus the momentum part, PA plus PB whole square. That must be equal to E1 plus E2 whole square minus P1 plus P2 whole square. Now, the important point is that particle B was at rest and EA was coming with certain energy and momentum. And what is threshold energy? This is the required energy of the particle to have desired final states. That means we want the existence of 1 and 2. Existence means these 1 and 2 should exist or would exist with rest masses of the particles. Therefore, what we need First is the particle 1 having rest mass energy m1 without any kinetic energy, particle 2 with rest mass energy m2 without any kinetic energy. Thus, the existence of these particles. Therefore, the right hand side will be m1 plus m2 whole square without any momentum. We don't require, because the threshold energy is the minimum energy required to have desired number of particles in the final state. Without any kinetic energy, just we need the existence of 1 and 2. While on the left hand side, if you notice, we have EA square plus EB square plus twice EA, EB minus PA square minus PB square minus twice PA dot P. This is the left hand side. Now notice that since E square is P square plus M square, therefore EA square minus MA square will give me EA square minus PA square will give me MA square. EB square minus PB square will give me MB square. Then particle B is at rest. Therefore, this guy will be 0 and EB will be MB. Therefore, what we will have on the left hand side, MA square plus MB square plus twice MBEA. This will be my left hand side. Therefore, I am writing the left hand side as EA MA square plus MB square plus twice MBEA. And the right hand side is simply M1 plus M2 whole square. Therefore, we can write here, as you can notice, we can write EA as equal to M1 plus M2 whole square minus MA square. EA will be equal to M1 plus M2 whole square minus MA square minus MB square upon twice MB. This will be the threshold energy of the reaction, and that means this will be the energy that the particle A should have to have 1 and 2 in the final state if B is the target particle. And this EA will consist of the kinetic energy of the particle A and the rest mass energy. Therefore, what will be the kinetic energy of the particle A? That will be this quantity minus MA. Therefore, what you can play with? You can play with the kinetic energy of the projectile. Therefore, since B is at rest, therefore, whatever you want in the final state, accordingly, you have to give the kinetic energy to the projectile. Therefore, what is the kinetic energy of the projectile? The kinetic energy of the projectile is TA, that is equal to M1 plus M2 whole square minus MA square minus MB square upon twice MB minus MA. Now, instead of 1 and 2, if I say that I want to have electron, proton and pi 0 in the final state, then here it will be mass of the electron, mass of the proton plus mass of the neutral pion square minus Me square minus MP square upon twice MP minus Me. That will be the kinetic energy of the projectile A. Therefore, if we have two particles, then we have M1 plus M2 whole square. If we have three particles, then that will be M1 plus M2 plus M3 whole square. If we have four particles, then that will be M1 plus M2 plus M3 plus M4 whole square. That means with the increase in the first term on the right hand side, M1 plus M2 plus M3 plus M4 etc., you can have the desired number of particles in the final state. And this EA is known as the threshold energy of the reaction, and TA is known as the minimum kinetic energy of the projectile A to execute the reaction. Similarly, I can take another example. Say here I am talking about I have 1 plus 2 plus 3 plus 4 in the final state. Then my PA plus PB whole square will be P1 plus P2 plus P3 plus P4 square, and then that means TA will be equal to this much. They are the same as what we did for the two particles. We can do it for n number of particles. That means I can write TA for n number of particles as M1 plus M2 plus dot 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 Mn whole square minus Ma square minus Mb square upon twice Mb minus Ma. This will be the required kinetic energy of the projectile A. Now, let us take a few examples to understand it more lucidly. And suppose I am talking about a process P plus P going to P plus P plus P plus P bar. Now, if you notice, this is my A, this is my B, this is 1, these are 1, 2, 3 and 4 different particles. Then recall the definition. TA is P M1 plus M2 plus M4 square minus MA square minus MB square upon twice MB. And that means here, since antiproton has the same mass as that of proton, therefore there are 4 masses of the protons here, 4 times the masses of the proton, minus 2 MP square for this particle, MP square for another particle. Therefore, this is MP square upon twice MP. And this is nothing but 7 MP. Therefore, the kinetic energy required for the particle A is 7 MP. Minus, if you recall, this is the energy of the particle A. This is the energy of the particle A, 7 MP, and then the kinetic energy of the particle A will be 7 MP minus MP, and that means this will be 6 MP. Therefore, the energy of the projectile A should be 7 MP. 7 MP means 7 into 938.2 MeV. And that will be the minimum energy required to have 3 protons and 1 antiproton in the final state. Therefore, the threshold energy for the reaction is 7 into 938.2 MeV. Similarly, let us take another example. Say I am talking about a gamma P giving rise to P plus neutral pion. Now, if you see this, I am talking about gamma P going to P plus a neutral pion. Then E gamma will be PP in MP plus M pi whole square minus MB square upon, because there should be M gamma square, but rest mass of the gamma is 0. Therefore, we are not taking into account, upon twice MP. That means this is equal to MP square plus twice M pi MP plus M pi square minus MP square upon twice MP. And that means this will be equal to M pi plus M pi square upon twice mp. This will be the threshold energy of the reaction, the energy dash the photon should carry. And now you know that mass of the neutral pion is 135 MeV plus 135 square upon 2 into 938.26. This will be the required energy for the reaction to take place. Similarly, you can take another example. Say, I am talking about E minus plus P going to E minus plus P plus pi 0 plus pi plus pi minus. Now what we know is that the antiparticle of pi plus is pi minus. That means the masses of these particles are roughly 140 MeV. This particle's mass is 135 MeV. This particle is 938.2 MeV. This is 0.5 MeV. Therefore, you can obtain the required energy of the electron to have 3 pions in the final state, and this you can obtain as E. This will be equal to mass of the electron in the final state, mass of the proton in the final state, mass of the neutral pion in the final state, 2 times mass of the pion, because pi plus has got the same mass as that of pi minus, and then mass of electron square minus mass of proton square upon twice mass of the proton. This will be the required energy of the electron to have 3 pions besides electron and proton in the final state. This is how we obtain the threshold energy of the reaction. Therefore, and this concept is important, that when you want to see a desired number of particles in the final state, then the energy of the projectile should be high. Now, the other type of experiments that is done is the center of mass experiments, where the particles from both the directions come with the same magnitude of momenta, and then they collide. And that case we will take later in this series of lectures. Now, we were talking about the conservation of different quantities in particle physics. We have discussed conservation of energy, we have discussed conservation of linear momentum, then we have the conservation of charge. As I have told you that the total charge in the initial state must be equal to the total charge in the final state. That means we have discussed various examples like this. Pi minus P can give us pi 0 plus n in the final state. Here the total charge is 0. Here the total charge is 0. Or what if I am talking about a delta plus plus decay, then it will decay to P plus pi plus. It cannot decay into P plus pi 0 because charge is not conserved. It cannot decay into n plus pi plus because charge is not conserved. Therefore, we have to take care of the charge conservation, and this is the basic requirement of the nature, and these are the 4 conservation laws: energy, linear momentum, angular momentum, and charge, which have to be conserved, and then we have additional 3 in the standard model of particle physics. Then let us come to the conservation of total angular momentum. As you know, the need of total angular momentum came when it was found that the Hamiltonian for the electron was not commuting with the angular momentum operator. This was not 0, because what this tells us that the simple physics is the following, which you can see from any textbook on quantum mechanics like Schiff or Sakurai or any other book, basic book, which tells you that a quantum number associated with the operator will be conserved quantum number if the operator commutes with the Hamiltonian of the system. Let me repeat it. What I am telling you, that a quantum number associated with the operator will be a conserved quantum number. That means conserved means that will be experimentally observed. That will be a reality that one will see in the experiments. If the operator commutes with the Hamiltonian of the system, what was found that the Dirac, if you take the Dirac Hamiltonian for the relativistic Hamiltonian for the electron, it does not commute with the orbital angular momentum operator. That means the quantum number of the associated with orbital angular momentum operator is not conserved quantum number, is not the complete quantum number, because we know from classical physics that orbital angular momentum exists. Then that means that is not the full story. And therefore, what was found that if we add a term like this, then the Hamiltonian of the system commutes with this full operator, which consists of orbital angular momentum operator and the spin angular momentum operator. And this constitutes the total angular momentum operator. Therefore, it is not that orbital angular momentum independently commutes with Hamiltonian, spin angular momentum operator commutes independently with the Hamiltonian. It is only that the total angular momentum operator commutes with the Hamiltonian operator, and therefore the quantum number associated with the angular momentum operator will be a conserved quantum number. And this was used to understand a Stern-Gerlach experiment. It is used if suppose the orbital angular momentum is 0 and there is a finite spin angular momentum of the particle, or the spin angular momentum is 0 if then you have the total angular momentum as the orbital angular momentum of the particle. Therefore, these are the special cases where you are talking about the ground SS. For example, I am talking about ground SS state, which corresponds to L equal to 0. Then the total angular momentum operator will only consist of spin angular momentum. Similarly, if I am talking about pions are spinless particle, then the angular momentum the total angular momentum operator will be just the orbital angular momentum operator. Therefore, the important point is, in general, it is the sum of orbital and spin or angular momentum that is the full operator, and that commutes with the Hamiltonian of the system, and that we should take care of in mind. And then suppose I am talking about a reaction A plus B going to say 1 plus 2 in the final state, then we can understand that A plus B going to 1 plus 2 in the final state, we have JA, JB, J1, J2. Then its value will go from JA minus JB to JA plus JB in steps of unity. Similarly, on the right hand side, the values will go from J1 minus J2 to J1 plus J2 in steps of unity. And that means when we will say that angular momentum will be conserved in this process, when suppose on the left hand side we have, after combining A and B's angular momenta, we have obtained a value something like 1, 2, 3. On the right hand side, it's not necessary that the values will be 1, 2, 3. Even if it is 3, 4, for example, by adding the two angular momenta for 1 and 2, then what we have a common 3 here, and we will say that angular momentum is conserved in such process. We will take more examples of this angular momentum conservation while discussing isospin algebra, because the isotopic spin algebra was developed in parallel to the angular momentum algebra. Therefore, we will see that how we can take care of the fact that the total angular momentum of the system should be conserved, and then we also take the projection of these angular momenta like MA, MB, which we algebraically sum, and we will see in isotopic spin angular momentum algebra how to combine the projections. Therefore, this is the total angular momentum operator is the complete operator, and the quantum number associated with this is the conserved quantum number. Then finally, we have already discussed in great detail about the conservation of baryon and lepton numbers. Therefore, this is how we consider the conservation of quantum numbers in particle physics. Those quantum numbers we call as exact conservation laws, where we have energy, linear momentum, total angular momentum, charge, lepton number, baryon number, and finally one that should be there is CPT. These three operators taken together. Therefore, we have charge conjugation, parity, and time reversal taken together. Then we have approximate conservation laws. Now, these laws were introduced to understand processes and to classify them into electromagnetic interaction, strong interaction, or weak interaction processes. But mind it, first of all, if I have been given any process, first we will check energy conservation, we will check the lepton number conservation, baryon number conservation, and charge conservation. If these we are obeying, then we will go to see that whether that process is possible through a strong interaction, electromagnetic interaction, or weak interaction. Therefore, these 7 conservation laws, they have been given by, say, hand. For example, you can say broadly that they have been given by hand, and they have been given to classify the different processes which have been observed in nature. And the first one that we will deal with will be the isotopic spin and the third component of isotopic spin. This was, as I am telling you, that this was developed in analogy with the total angular momentum operator, and this was developed in analogy with the z component of the projection of the angular momentum operator. Either you call it Jz or Iz. Therefore, you have isotopic spin. Isotopic spin is not a vector in ordinary space. It is in hypothetical charge space. Okay. Then we have strangeness. Third, we have discussed about the strange particles. We have discussed about the different strangeness quantum number that we assign to the strange particles. We have discussed at length why these particles are called strange particles. Then we have charge conjugation operation, parity operation, charge conjugation and parity taken together, and finally time reversal operation. We will discuss these in the next series of lectures, when we will start talking about the symmetry and its importance in particle physics. Therefore, why this idea of isotopic spin came? Now, if you look at the example of mirror nuclei, what are mirror nuclei? Mirror nuclei are those nuclei having the same mass number, but the proton number of one is the neutron number of the other. This is N and this is Z, this is A. Proton number of one is the neutron number of other, and similarly neutron number of this nucleus is the proton number of this nucleus. and that is called as mirror nuclei. There are many mirror nuclei which have been observed in the different experiments. Here I have given a few examples like 6 carbon 13, where we have 6 protons and 7 neutrons, and 7 nitrogen 13, where we have 7 protons and 6 neutrons. Similarly, we have 4 beryllium 7 and 3 boron 7, 8 oxygen 17 and 9 fluorine 17. And what has been observed that if you look at them, then what's the difference? The difference is in the proton number. And when I'm talking about the difference in the proton number, that means the difference is in the Coulomb energy. That means we are talking about electromagnetic interaction, and because of the electromagnetic interaction, these two masses of these two mirror nuclei are different. But if I switch off the electromagnetic interaction, that means I take care of this extra Coulomb energy part, then what has been found that the masses of these two mirror nuclei are almost the same. Whether I'm talking about carbon nitrogen, or I'm talking about beryllium boron, or I'm talking about oxygen and fluorine, or similarly other mirror nuclei, those have been observed in nature. So therefore, the difference in mass of the two nuclei is due to the different Coulombic interactions, that means electromagnetic interaction. Now, if we switch off the electromagnetic interaction, then the masses of these two nuclei have been found to be exactly the same. Why this is important? Now, had these strong interaction be different for the protons and neutrons, then one would expect that the masses of these two mirror nuclei will be different, because a strong interaction is treating protons and neutrons differently. But since when we are switching off the electromagnetic interaction and masses of the nuclei are coming out to be the same, then that means from the eyes of strong interactions, these protons and neutrons are one and the same particle. And that gave rise to the concept of charge independence of nuclear forces, which says that the interaction between the two protons is of the same strength as the interaction between proton and neutron, or the interaction between the two neutrons. Okay? Therefore, from the eyes of strong interaction, protons and neutrons, they are not different particles. Simply speaking, what it says in layman language, that if I have got a magnetic field, then only if I will pass through these protons and neutrons, we'll be able to know, oh, this is proton, and this guy which is going on a straight path, that is neutron. But if I switch off the magnetic field, I have switched off the electromagnetic interaction, then there is no way to distinguish between a proton and a neutron. Similarly, if you look at the binding energy of tritium and helium-3 nuclei, which are quite similar if you take Coulomb energy into account. Therefore, the charge independence property is not simply an invariance under the exchange of proton with a neutron, rather it is the invariance under isotopic spin, or the other name of that is isospin. Isotopic spin was proposed for the first time by Wigner Heisenberg in 1932, where he proposed that the proton and neutron should be considered two states of the same particle, and he gave a common name to them as nucleon. Therefore, he coined the word nucleon and said that protons and neutrons are the different states of this particle. And therefore, what was argued that we assign an isotopic quantum number half to the nucleon, and this half has got two projections. I3 is equal to plus half for the proton and minus half for the neutron. And therefore, similarly, when we talk about pions, then pi plus, pi 0 and pi minus, they are different particles when we have switched on the electromagnetic interaction. But if we are passing these particles through, that means if we are passing these particles through the magnetic field, then only one fellow will go in this direction, another guy will go in this direction, and the neutral pion will go in this direction. But if there is no magnetic field, then what has been observed, that there is no way to distinguish among pi plus, pi 0 and pi minus. And that is why we assign an isotopic spin quantum number 1 to these pions, +1 for the pi plus, 0 for pi 0 and -1 for pi minus. These are the projections of isotopic spin. So the algebra for isotopic spin was developed with the same analogy as that of the total angular momentum. The isotopic spin quantum number is assigned to the hadrons. Mind it, this is assigned only to the hadrons, the particles which participate in the strong interaction. Hadrons means we are talking about baryons and mesons, the particle which participate in the strong interaction. Let us stop here and we will start from this place in the next class. Thank you very much.